Have you ever wondered why a pressure cooker doesn't start whistling the moment you switch on the stove? Why does it wait for some time before releasing steam? And what mathematical equations govern this everyday kitchen appliance? In this video, we'll answer all these questions using a fascinating problem from the thermodynamics section of Irodov's book on problems in general physics. We'll solve the problem, understand the physics behind pressure cookers, and as always, rise above the maze of equations to see the bigger picture. So stay till the end. Here is the problem. Two identical vessels are connected by a tube containing a valve. The valve allows gas to pass from one vessel to the other only if the pressure difference exceeds 1.1 atmospheres. Initially, vessel A contains an ideal gas at a pressure of 1 atmosphere and a temperature of 27 degrees Celsius. The second vessel B is completely evacuated. Both vessels are now heated to a temperature of 107 degrees Celsius. The question is, up to what value will the pressure in the empty vessel increase? Pause the video for a moment and see if you can solve it yourself. Let us first understand what happens physically. Initially, pressure in the first vessel is 1 atmosphere. The pressure in the second vessel is 0 atmosphere. Therefore, the pressure difference is 1 atmosphere. But notice that the valve opens only if the pressure difference exceeds 1.1 atmosphere. Since 1 atmosphere is less than 1.1 atmosphere, the valve remains closed. No gas flows. This is very similar to a pressure cooker. Initially, as we heat the cooker, steam is generated, but the whistle does not lift immediately. The pressure inside the cooker must first build up beyond a certain threshold. Only then does steam begin to escape. Exactly the same thing is happening in this problem. Since the valve remains closed initially, all the gas stays inside the first vessel. The volume and the amount of gas remains constant. Therefore, according to the ideal gas law, at constant volume, pressure is directly proportional to temperature. The temperature rises from 27 degrees Celsius or 300 Kelvin to 107 degrees Celsius or 380 Kelvin. So the initial temperature is 27 degrees Celsius. When we convert it to Kelvin, we get 300 Kelvin, and it rises to 107 degrees Celsius, which is 380 Kelvin. Now, we already discussed that pressure is directly proportional to temperature, which means that P1 upon T1 is equal to P2 by T2, and this can be written as P2 is equal to P1 times T2 by T1. Substituting the values, P2 is equal to 1.267 atmospheres. So after heating, the pressure in the first vessel becomes 1.267 atmospheres. The second vessel is still empty. Since the pressure in the vessel A becomes 1.267 atmosphere and the pressure in the vessel B is 0 because it is empty, the pressure difference between the two becomes 1.267 atmospheres. Now this pressure difference exceeds the threshold value of 1.1 atmosphere. Therefore, the valve opens and gas starts flowing into the second vessel. But for how long will gas continue to flow? Gas will continue flowing until pressure difference falls back to exactly 1.1 atmosphere. Because if the pressure difference becomes smaller than this value, the valve closes. Let the final pressure in the two vessels be PA and PB. Then PA minus PB will be equal to 1.1 atmospheres. This is our first equation. Now let us use conservation of mass. Initially, all the gas is in the first vessel. After the valve opens, the gas redistributes itself between the two vessels. No gas escapes from the system. Therefore, the total number of moles remain constant. Since the final temperature of both vessels is same, that is 380 kelvins, we can write initial pressure times volume equals This is the initial pressure times volume, and this equals final pressure in vessel A times the volume of vessel A plus final pressure in vessel B times the volume of vessel B. Since the vessels are identical, the volumes cancel out. And we get a new equation, PA plus PB is equal to 1.267 atmosphere, and this is our second equation. We now have two equations. The first equation was PA minus PB is equal to 1.1 atmospheres and PA plus PB is equal to 1.267 atmospheres. This first equation, we got it from the condition for threshold pressure difference that is given to us in the problem, and the second equation came from conservation of mass. If we solve these two equations and we subtract the first from the second equation, it gives us 2 times pressure in vessel B is equal to 0.167, and pressure in vessel B then becomes 0.0835 atmosphere. So pressure in the initially empty vessel becomes 0.084 atmospheres. And that is the answer. But what is the bigger picture here? This principle illustrates a very important engineering principle. Many real engineering systems operate using threshold mechanisms, pressure cookers, safety valves in boilers, pressure relief valves in pipelines, even hydraulic systems. Nothing happens until a critical pressure difference is reached. Once that threshold is crossed, the system responds. The humble whistle of a pressure cooker is therefore not just a kitchen sound. It is thermodynamics in action. The next time you hear that whistle, remember that behind it lies the ideal gas law, pressure thresholds, and some beautiful engineering. Did this connection between an Irodov problem and a pressure cooker surprise you? Let me know in the comments. And if you enjoyed this video, please like, share, and subscribe to our channel. I'm building this channel around mathematics, physics, scientific ideas, and explaining from first principles. And if there's a topic you've always wanted to understand, let me know in the comments. It might become a future video. Thank you for watching, and I'll see you in the next video.